Hello everyone, I hope you all are well. In this video, we'll talk about Euler path and circuit. So let's begin. Euler path is a path in which every edge is transferred exactly once. So if you have a path like this, and if you have a graph something like this, if I start the path from C, then the path goes from C to F, and then from F to D, then from D to E, then from E to A, then from A to D, and then finally from B to E. So in this way the path has transferred every edge of the graph, and such kind of path is called Euler path. Euler circuit. What is an Euler circuit? In Euler path, if we take the initial and final vertex to be same, then that becomes Euler circuit. If you see in this example, if I start from B, then B to E, E to C, then from C to A, then from A to D, and then from D to B. So the path started from B and it's ending at B. So this is an Euler circuit. It is traversing every edge of the graph. It becomes an Euler circuit. A graph in which either there is Euler path or there is an Euler circuit, that kind of graph is called an Eulerian graph. So there was a problem posed by the people of Königsberg. In Königsberg, there are two islands. Here you can see there are two islands, and there are some river banks around these two islands, and these islands are connected to these river banks by 7 bridges. Here you can see 1, 2, 3, 4, 5, 6, 7. There are 7 bridges here. So they are connected with each other through these 7 bridges. So they posed the problem, people of Königsberg posed the problem that if it is possible to find a trail starting at one of the 4 islands that crosses each bridge exactly once, in which you return to the same island you started on. So if it is possible to reach to every island and every bridge, and and you come back to the same point from where you started, is it possible or not? So in the Euler has given solution to this problem through a theorem. So we have this theorem. We'll study this theorem first to get the solution of Königsberg problem. So the theorem is: a connected graph G has a Eulerian circuit if and only if every vertex of G has even degree. Okay, so we'll prove this theorem that Euler circuit exists in a graph if and only if every vertex of G has even degree. So let us assume first that G is a connected graph having Euler circuit. We will show that every vertex of G has even degree. Let consider A be any vertex of G from which the circuit starts. So A is any vertex of G. As there's a Euler path, Euler circuit is there in this graph. So A will be connected to some other vertex B, and it will transfer some path and it will return back to A. Okay, so in this way, what is the degree of A here? You can see degree of A is 2. The path starts from A, Euler path starts from A, it goes to some places, it again return back to A. So in this way the degree of A is 2, which is even. So if the path ends here, if the circuit ends here, then it is of even degree, the degree of A is even. Okay, but if it doesn't end here, then again it will go to some other point, it will move to some other point. Okay, and it will again return back to A. Okay, because degree of it will again return back to A because it has to complete the circuit. So initial and final vertex should be same. So if it goes to some other vertex, it will again return back to A. So in this way degree of A is again 4, which is even. Okay, if the circuit ends here, then this is then we have proved that degree of A is 4, which is even. If the circuit doesn't end here, then again it will move to some other point, again it will come back, again it will be even, right? So in this way, in every case, the degree of A will be even, and we have taken A to be any arbitrary vertex of G. If we take any other vertex of G, then again that vertex will also will have even degree. In this way, every vertex of G will have even degree, and this proves one way of the theorem. Now let's do converse of the theorem. Let us assume that G with V vertices and E edges has even degree. We will prove that G has Eulerian circuit. We will be using induction here, okay? So let A be any vertex of G and A has even degree. Let A be any vertex of G. Because A has even degree, it will be connected to Y and Z, okay? It is connected to Y and Z. It will be definitely connected to 2 or more than 2 vertices, okay? So what I'll do, I will remove AY and AZ. I have removed AY and AZ and I'll join Y and Z. Okay, so this is a new graph G dash. We got a new graph G dash. This graph G dash has same number of vertices as that of G, but it has one edge less than that of G. Okay, it has same number of vertices. V vertices remain same in G dash, but number of edges is one less than the number of edges in G. So it has E minus 1 edges. By using induction, we will assume that G dash has Eulerian circuit. So we will assume that G dash, the graph which is obtained by removing these two edges and joining these two vertices, that graph G dash has Eulerian circuit. So the Eulerian circuit will be something like this. It will start from here, it will go around that, and it will again come back here. Okay, so it has some Eulerian circuit. So from this Eulerian circle, we'll make the Eulerian circuit of G. Now Y also has even degree, Z also has even degree, and A also has even degree. What we can do, we can remove this edge from G dash. We can join these two because they have even degree, okay? And to keep the even degree of A even, we'll join A and Z also. So if then I again trace my Eulerian circuit, then Eulerian circuit starts from Y, it goes like this, again it come back to Z. Now instead of going here, what will happen, it will go to A and then it will again come back to Y. So there will get a Eulerian circuit in G, right? So the graph will look something like this. So it has got we have got a Eulerian circuit in G, okay? So and it can also happen that from if the graph starts from A, then it goes like this, again come back at A, and it goes like this, right? Because A has even degree. So we have got a Eulerian circuit in G. So every graph which has Eulerian circuit must have the degree of each vertex as even, and converse is also true. Let's just come back to our 7 bridge problem. Okay, let's just name the land masses as A, B, C, D. Let's take this as A, this as B, this landmass as C, and this landmass and D. And here you can see A is joined to C with the bridge this one, C is joined with B with another bridge, then A is joined with C with second bridge, then C is connected to B with another bridge, then A is connected to D with this bridge, then B is connected to D is with this bridge, and C is connected to D with this bridge. So there are 7 bridges and they are connecting A, B, C, D, the land masses. So this problem looks something like this. If we consider A, B, C, D as vertices and the lines as edges, we get a graph like this. Okay. So here we will look at the degree of each vertex. Degree of A here you can see A is connected to 1, 2, 3. So degree of A is 3, degree of B 1, 2, 3, degree of B is 3, degree of C 1, 2, 3, 4, 5, degree of C is 5, and degree of D 1, 2, 3, degree of D is 3. So every vertex has odd degree. So by that theorem, this graph cannot have Eulerian circuit. So there is no solution to 7-bridge Koenigsegg problem. So it's not possible to find a trial starting at one of the 4 islands that crosses each bridge exactly once, and so that you return to the same position. So it has no solution. Now from that theorem we get another result. The result says a graph has Euler path. A graph has Euler path if and only if each vertex has even degree, or only 2 vertices are of odd degree. So you just try to prove this result. If you didn't get it, please let me know in the comment section. I'll make video on this result. Okay, I'll give you hint for this. What you can do, you can take the initial vertex and final vertex having the odd degree and other vertices as even degree. Okay, just try to do this. I hope you have understood everything in this video. If you have any doubt, you can ask me. You can put your question in comments. Thanks for watching this video. Have a good day.